I'm presenting this talk on my PhD and I'm supervised by Dr. Rickman and Professor Mori. My paper is about objective tailorability prediction using fast equipment. Tailorability problems facing the men's suits are mainly poor lapel molding and a puckered seam. These can be predicted prior any manufacturing using the fast equipment. Mainly on shell fabrics, we test for mechanical properties as well as physical and dimensional properties. And from these we can tell if this fabric is going to suffer a tailorability problem or not during manufacturing. From the mechanical properties and physical properties, we apply them on such control chart where each of the mechanical properties is represented by one parameter. The gray zones which we can see, they are representing tailorability problem. So any fabric getting a mechanical property, for example for formability, which lies within the gray zone, it will suffer seam pucker. And these are done in the manufacturing on shell fabrics. What I'm talking about is the men's suit, and 60% of the men's suit is made up of composite fabrics. Composite fabrics which I'm talking about are shell fabrics added to it different types of interlinings. If we can see the figure, we can see that this is a portion of a men's suit and it contains at least 3 parts of 3 different interlining. These are all fusible interlinings. Due to the adhesive dots within interlining, as well as in some cases, the layers are restricted within a composite, different mechanical properties for these composite fabrics compared to the shell fabrics. The aim of the study is to investigate the effect of different types of interlining on composite fabric mechanical properties, as well as the effect of these interlinings on the tailorability problem, particularly seam pucker and lapel molding appearance. Finally, I'm aiming to investigate the suitability of existing fast parameters and gray zones for prediction of seam pucker and lapel appearance. During the experimental, I've tested 35 composite fabrics. These are made up of shell fabrics, 15 shell fabrics, and 3 different types of interlinings: vertically stitched interlining, and high adhesive dot density interlining, and finally a low adhesive dot density interlining. So the same set of shell fabrics have been fused to these 3 different interlinings. So we have 3 different sets of composite fabrics tested all on the fast equipment for their mechanical, dimensional, and physical properties. After I've tested them, I've tested them as well subjectively using 7 experts in the field. The AATCC, as you can see on the above figure, has been used for the assessment of seam pucker, while the lower figure has been used to assess the lapel molding appearance on ascending ranking, where 1 means the best lapel appearance and 10 means the worst. We've been looking for the lapel appearance in terms of if it's sticking out or it's bubbling or even puckered, and that's how assessors were giving their judgment. Finally, from The subjective assessment of the apparel appearance and seam pucker, we have tried to figure out the linearity between these tailorability problems and the mechanical properties for composite fabrics. For example, I've tested the seam pucker problem with formability, mechanical property, and linear regression using SPSS has been used. First part is the effect of interlining on the different mechanical properties, especially extensibility, formability, and shear rigidity. If I'm talking about the extensibility, different interlinings vary in the results of the composite fabrics. If we're seeing the rectangle down on the screen, these are the composite fabrics of vertically stitched interlining. They're having the minimum extensibility value. They got value of extensibility equal to their interlinings, whatever is the shell fabric extensibility. So in fabric 2, the shell fabric is very high in its extensibility. However, when it was fused to the vertically stitched interlining, it got very low extensibility value equal to the rest of these composite fabrics. Again, with the composite fabric C, the purple one, we can see that it gives very high extensibility values. This is because of the low adhesive density or dot density within this interlining. For shear rigidity, again, the different parts of interlining gave different values for the resultant composite fabrics, and the vertical stitched lines exceed the values for shear rigidity of their shell fabrics. The high adhesive dot density within interlining gave higher rigidity. This is because with a high number of adhesive dots per centimeter square, the bigger the number of yarns pressed, and by turn the angular movement is minimized, giving high shear rigidity values. For formability, the less extensible the interlining is, the lower its composite's formability. With formability is a product of extensibility multiplied by bending rigidity. We found that the bending rigidity didn't contribute at all to this parameter when it comes to composite fabrics. The extensibility of the interlining possessed high formability value to these composite fabrics. After one finished with the objective measurements for formability, extensibility, and shear rigidity, and by testing these composite fabrics subjectively, 50% of these fabrics were found to suffer seam pucker problem, and these were different than those of their shell fabrics. 5 out of the 20 tested composite fabrics for this particular tailorability problem, the apparel appearance, found to be not acceptable, subjectively assessed by our judge. From the linear regression, we found that the already existing fast parameters for shell fabrics are different than those we have with our composite fabrics. The fast parameters are found to be not linearly correlated to their related tailorability problems. For example, the seam pucker is not linearly correlated to the formability parameter as it is for shell fabrics. Again, with the lapel molding appearance, it is said to be linearly correlated to extensibility property in terms of shell fabric, but this was not the case with our composite fabrics. In conclusion, composite fabrics are having different chemical properties due to the presence of the interlinings, particularly high yarn intersection of the adhesive dots and the vertical stitch lines within the interlining. We are recommending that the composite fabrics, mechanical properties, as well as their physical properties and dimensional properties have to be tested side by side with the shell fabrics. The development of composite fabric fast fingerprint chart for the prediction of tailorability problems is in need. This should be through non-linear correlation between the tailorability problems and the different deformation parameters for composite fabrics. Thank you so much.
Thank you for your presentation. Dr. Taylor has not been able to join us here.